All right, so now on to the next couple examples. Now, these are important because these are in our factored form. And if you remember us talking about the multiplicity, we can only talk about the multiplicity of our zeros when they're in the factored form. So these next three examples are great because it's going to help us really easily identify the multiplicity of our zeros, but they're really bad in the fact that they're not as explicit as far as determining the end behavior, because now we have to determine what is the leading term, right? When it was in standard form, identifying the leading term was, rather simple. In these three examples, we don't really have them. We don't have them multiplied out. Now, obviously, we could go out and multiply everything out, and the examples I chose are not that crazy. You could easily just multiply out, put it in standard form, and then go ahead and find the end behavior. But we can do a little bit of just like understanding of multiplying out binomials, and we can kind of do this a little bit rather quickly without actually having to multiply everything out. So the way that I do this, or way to think about this, is if you're multiplying a binomial times a binomial, we know that's going to give us a quadratic trinomial. Basically, we know that the highest power, when we multiply these out, we know that the highest power that we're going to get is 2, because x times x gives us x squared. We're not going to ever get x cubed in this example, or x to the 4th, whatever else. So our highest power, or our highest exponent, we could say, is x squared. And then whatever the rest of it is, doesn't really matter in this case. We're not trying to figure out what it is in standard form. We're just trying to find the leading term. That's all we care about, the one that has the highest power. So by multiplying these two, I would get a leading term of x squared. And then I would have to still multiply it by x minus 3. Now, if I multiply some quadratic trinomial, or whatever this is, times x minus 3, now the new highest term that I'm going to get is going to be x squared times x cubed, or x, which would be x cubed. Now, again, I don't know what the rest of it is, and I'm not even going to spend my time finding the rest of them, because if you notice, when we do these, when we're finding the end behavior, we're only concerned with our leading term, right? So just by multiplying this out, I can determine my leading term here is x cubed. So now I can find the end behavior from here. The end behavior x cubed, let's see, that is a degree, which is odd. The degree is 3, and my leading coefficient is 1, which is positive. So going back to my leading coefficient test up here, if my degree is odd, but my leading coefficient is positive, it's going to fall to the left and rise to the right. So I'll just go ahead and write in there. Falls left, rises right. Okay. As far as now, we can determine that the maximum number of zeros in this case is going to be 3, and the maximum number of turning points, or extrema in this case, is going to be 2. Now, I talked about finding the multiplicity, when possible. We can identify the multiplicity here, because if you remember from our notes, let's just kind of go back to the notes here on multiplicity. The multiplicity, when you have something as a linear factor, that means you have factors multiplied by one another, which we have in that example. When I have something in the form x minus c raised to the m, where c and m are numbers, m is represented as our multiplicity. And if m is even, that means the graph bounces, or if m is odd, that means the graph is going to cross at our value. So in this case, you can see here I have x minus 1. So we could say 1 is equal to c, right? Now, you might be thinking, well, there's no number that it's being raised to. Well, we don't write it if it's not there, or if it's a 1, because if it's just raised to the 1, it's just there. So we usually don't write it. But you can see that these are all in the form. Each of these factors are in the form x minus c raised to the m. So in this case, we actually have a 0 at x equals 1. Because c is equal to 1. So at x equals c, which in this case is 1. So we have a 0 at 1, and we have an odd multiplicity. So that means the graph is going to cross at 1. In this case, c is equal to negative 2, because remember it's x minus c. So since it's, this can also be written as x minus a negative 2. That would be x plus 2, right? So therefore, x is equal to negative 2 in this case. So we have a 0 at negative 2. That crosses because that's odd multiplicity. And then we have another 0 at 3 that crosses with an odd multiplicity. So let's go and take a look at the graph here and just double check to make sure that that is correct. Yes, we can see that we have a 0 at negative 2, at 1, and at 3, right? And if we zoom out here a little bit, we can also see that there are 2 turning points, which we discussed, which would be the true case, and also our end behavior falls left and then also rises right. Okay, now let's go and look at this next example. Now, this one isn't too bad, that again, to multiply this out, but we don't really need to, right? Again, if we were just going to expand x plus 1 squared, remember that's x plus 1 times x plus 1. So therefore, this would be f of x equals negative x times, x squared dot, 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 dot. All right, now even though you should know what that product is, and even though I could write it in there, I'm not even going to spend my time going from there. I just want to find the leading term. Now, if I was to multiply negative x times x squared, that would end up giving me a leading term of negative x cubed. And then again, you'd have to multiply by all the rest of the terms. But again, now in this case, we're just concerned with looking at our end behavior and determining the maximum number of zeros in extrema. So in this case, our end behavior, since this is odd and this is negative, it's going to rise to the left and it's going to fall right. And again, this is based on the leading coefficient test that we just took a look at. We can see that my zeros, or the degree is 3, so the maximum number of zeros is 3, and the maximum number of extrema is 2. Okay. Now, are these again written in your as multiplicity? Are zeros in a factored form? And yes, they are. So let's go and take a look at here how we can understand these written as your zeros. Now, we could rewrite this by taking out this negative. So I could factor out the negative. I could write this as x minus 0 raised to the first power times, an x times a negative 1 squared. Okay? So now in this case, what we can see here is, again, this negative, I want you to understand, is not really affecting our 0. It's going to be affecting the end behavior, obviously, and the shape of the graph. But the zeros is we're going to have a 0 or an x-intercept at 0, which is 1. And then we're also going to have an x-intercept at negative 1, and it has an even multiplicity, so that means the graph is going to bounce at negative 1, and it's going to cross at 0, because odd multiplicity crosses, even multiplicity, it's going to bounce. Now, notice again that the maximum number of zeros is 3. Looks like we only have 2 zeros, but this multiplicity is kind of like a repeated 0, and this 0 is being repeated twice. So if you kind of count up the multiplicity, 2 plus 1, you see that that equals 3. And the extrema is obviously going to be 1 less, and we'll see how that relates. So we go to the next one. And you can see here, as we kind of now zoom in, at negative 1, it bounces, and at 0, it crosses, which was true. You can see the end behavior of the graph rises to the left and falls to the right, which is true. And you can see that there are 2 turning points. We have that turning point at the 0, and we have the other turning point, at negative 1/3, which again falls in line with what we were talking about as far as the maximum number of extrema. All right, and then last but not least here, we have another one that we'd multiply by. This is going to be the exact same case. It's a little bit more difficult, so you probably definitely would not want to attempt to multiply it out, but you could. I mean, it's nothing wrong with it. But let's just go and again practice, what we'd get, negative 2x squared. Now, if we were to multiply this out, the maximum, again, leading term would be negative 3x times negative 3x, right? Because again, remember, negative 3x squared is just negative 3x plus 2 times negative 3x plus 2. So you'd have to do distributive property and blah, blah, blah. But again, we don't care. We only care about what's going to give us the highest term, highest binomial, which would be a positive 9x squared. And then we could do the rest of it, dot, 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 whatever, right? Now, if I was to multiply that again through, or multiply this negative 2x through, I would get a leading term of negative 18x to the 4th. So that's going to be my leading term. We can see that my degree is even and my leading coefficient is negative. So then based on the leading coefficient test, my graph is going to fall left and fall right. Okay, the maximum number of zeros in this case is 4, and the maximum number of extrema is going to be 3. To determine the multiplicity, again, we could also kind of look at this as a kind of look at this 0 and kind of see what exactly is happening here. So I could rewrite this f of x as, again, kind of factor out this negative 2. It's not really affecting my 0. That's really just a multiple. So I can negative 2 minus 0 squared, because x minus 0 is x, and then x squared is obviously just, x squared. And then I could write this as negative 3x plus 2 squared. Now, if we were to set each of these factors equal to 0 and find the zeros, we would have x equals 0. And then if we were to set this equal to 0, we would see this is going to be x equals positive 2/3. And again, I mean, I don't want to get too ahead of myself, but this is going to cross at this 0. But either way, what I want you to notice is we have maximum number of 4 zeros. We only have 2 zeros, right? But they both have a multiplicity of 2. And again, if you count up the multiplicity, 2 plus 2, that equals 4. Interesting, right? So let's go and take a look at the graph, see if I'm right on the positive 2/3 and 0, both bouncing on the graph, and then also my end behavior falling left and falling right. So let's go and check that, see how good I did. And there you go. Looks like it's pretty good. As I go ahead and zoom in here, we got 0, and we have positive 2/3. So obviously it got a little rounding, but it's there. And the graph falls left and falls right. And then also you can see that there are 3 turning points, right? So one less than our power, which is 3. That's the maximum number of turning points. And we have 2 zeros, though, when we have a max number 4. But again, since these both have an even multiplicity of 2, you add the multiplicities up, and that equals that maximum number, which is, again, very interesting. So that is kind of like the basic understanding, our ideas, guys, of our leading coefficient, and as well as when we're looking at a polynomial, how we can determine not only the end behavior, but also go and take a look at the number of zeros, the number of extrema, and then when it's in factored form, when we can look at more understanding the multiplicity. So now we'll just kind of talk about, now we'll kind of look into a little bit more, get in a little bit more in depth as far as finding actually the extrema and the x-intercepts, but that will come into using some technology in the next lesson.